Thank you. Thank you for the introduction. Thank you to the organizers for the opportunity to speak here. I'm happy to be doing so. And as Hank mentioned yesterday, so this is partly motivated by nearly the last payslip of Karma and Core. So I want to also thank both of you for the opportunity to work with you over the past few years. It's been an honor and a pleasure to do so. So thank you. So this talk will be based on joint work with both Karma and Core. We recently put a preprint on the archive titled Inducing Contractions of the Mother of All Continued Fractions. And this gives us a method of generating a bunch of new continued fraction algorithms from one particular dynamical system. And so this talk, the first few parts will be looking at this method and some of the continued fraction algorithms that are born out of this process. So to start, we've seen in previous talks regular continued fractions. So this is mostly the set notation. So each x in the real numbers has essentially a unique regular continued fraction expansion, which we'll denote by a0, a1, a2, etc. So each of these partial quotients, an is an integer, and we're assuming that they're positive for indices greater than 0. And we'll denote the regular continued fraction convergence by Pn over Qn. So this is the rational number that you get when you stop this expansion after n digits. And the digits of the regular continued fraction expansion are generated by the Gauss map, which we've also seen. So on the right is a graph of the Gauss map. It's defined by taking 1 over x modulo 1, and the digits an are computed using this function a of x, which is really the floor of 1 over x. So the nth digit in the regular continued fraction expansion of x is given by taking a of the n minus first point in the forward orbit of x under the Gauss map. And you can study the system dynamically. So there's an associated invariant probability measure that's absolutely continuous with respect to the Beg, called the Gauss measure. This has density 1 over log 2 times 1 plus x. This is named after Gauss, so he basically asserted its existence in an 1812 letter to Laplace, but it's unclear how Gauss actually came up with this measure. There have been several attempts to kind of derive this measure from scratch since then. One of these comes through the natural extension of the Gauss map, which was also mentioned by Hitoshi Nakada earlier today. So an explicit realization of the natural extension was given by Nakada, Ito, and Tanaka in the 70s and 80s. And the natural extension, in words, is basically the smallest invertible dynamical system of which the original underlying system is a factor or a subsystem. Okay? So here, the planar natural extension that was given in the 70s and 80s, the domain omega is really the unit square. And the map script g is a function from the unit square to itself, given explicitly as shown. So really in the first coordinate, you have the Gauss map again. And in the second coordinate, it's essentially the inverse of the Gauss map. So what this does geometrically, we take the domain omega and break it up into these vertical rectangles whose edges have endpoints 1 over n, and these horizontal rectangles also with edges points to the form y equals 1 over n. The Gauss map, the natural extension of the Gauss map will take the vertical rectangle vk to the horizontal rectangle hk up to sets of measure 0. So that's kind of geometrically what this map is doing. How is this related to the Gauss measure? So if we denote by pi the projection onto the first coordinate, as Hitoshi mentioned earlier, for a slightly different representation of the natural extension, we basically disintegrate to obtain the Gauss measure. So if we know the two-dimensional measure for this system, nu bar g, then the Gauss measure of a measurable subset of the interval is given by taking the pre-image of that interval and then taking the two-dimensional measure of this pre-image. And here, the density of this two-dimensional measure, nu sub g bar, is given by 1 over log 2, 1 plus xy quantity squared. So this is a slightly different representation than the one mentioned earlier by Hitoshi, but it's isomorphic to that one. Okay. So besides the regular continued fractions, there are several other continued fraction expansions and algorithms to produce these. So for the sake of this talk, I'll call these generalized continued fraction expansions. And these will be denoted with beta naught, alpha 1 over beta 1, alpha 2 over beta 2, etc. Here, beta naught can be a rational number, and the alphas and the rest of the betas are integers. We'll assume that the alphas are non-zero. There are several algorithms which produce a particular generalized continued fraction expansion for a given x, so for each x. So we've seen the regular continued fractions. There's also singular continued fractions, nearest integer, backward, optimal, and diagonal continued fraction algorithms. There's also a one-parameter family of continued fraction algorithms introduced by Nakada in 1981 called the alpha continued fractions. And this family actually contains the backward, nearest integer, singular, and regular continued fractions for various instances of alpha. There's another family that was introduced by Kraaikamp in 91 called the S-expansions. And these contain some of the alpha continued fractions, also the optimal continued fractions studied by V. Bosma, and the diagonal continued fractions. Okay, so I want to look at these two families a little bit more closely. The alpha continued fractions, so again, this is a one-parameter family defined for each alpha between 0 and 1. They're defined quite similarly to the Gauss map that we saw before, but now it's on the interval from alpha minus 1 to alpha to itself. And the map is given explicitly here. And you can check that if alpha is equal to 1, you actually recovered the Gauss map. So you can see that the Gauss map is in this family. And you can study these dynamically as well. So each G alpha has a unique, absolutely continuous invariant measure, rho alpha. And with this measure, the system is ergodic. Okay. So when Nakada introduced these in 81, he mainly restricted his study to alpha greater than or equal to 1/2, and essentially gave everything you would want to know about these systems for alpha greater than or equal to 1/2. So in particular, he was able to construct the natural extension for each of these systems for alpha greater than or equal to 1/2. And doing so, he was able to compute the density of this measure explicitly, and also give the entropy, the metric entropy of these systems for alpha greater than or equal to 1/2. But the case for alpha less than 1/2 has been a lot more difficult to study, and there have been several papers trying to understand what's going on for these values of alpha. In particular, several authors have tried to study the entropy of these functions as a function of alpha. And for alpha less than 1/2, this entropy function shows some self-similar and complicated structure, so it's been quite difficult to understand. There are points where it's not even locally monotone, but it is known to be continuous and even Holder continuous. And it's also been difficult to construct the natural extension for the alpha continued fractions less than 1/2. So this took over 30 years to build these natural extensions. This was done in a paper by Kraaikamp, Schmidt, and Steiner, so Tom Schmidt, rather than the Wolfgang Schmidt we've heard of many times in this conference. So this was done in a paper in 2012, where they gave the natural extension for the alpha continued fractions for all alpha. But it's kind of a theoretical construction looking at a certain orbit closure in that paper. Okay. Then the S-expansions introduced by Kraaikamp. So these are defined in 1991. And this gives a large collection of continued fraction algorithms that are based on coupling two acceleration techniques. So the first one is what's called singularization. And this is a method where you can sometimes take a continued fraction expansion, and from this produce a new continued fraction expansion whose convergents are a subsequence of the original convergence. So you can kind of accelerate by removing convergence. The second acceleration technique is induced transformations of the natural extension of the Gauss map that we saw before. So you basically fix some nice measurable subset of the domain, in this case delta, and look at the first return map to the subset delta, and just focus on the dynamics restricted to this subset. So you're accelerating things with this induced system. And the S-expansions use induced transformations to govern singularizations. So what I mean is that if you look at the orbit of a point x comma 0, and the nth point in the orbit lands outside of the region that you're inducing on, then you remove the corresponding convergent. Okay? So you kind of couple inducing and singularization to create new continued fraction algorithms that are accelerated versions of the regular continued fraction expansion. Okay, so I want to look at this picture again that I showed with these different continued fraction algorithms in these two families. You'll notice I've drawn it in such a way that these S expansions just overlap kind of the right half of the alpha continued fractions. This is intentional. So the S expansions contain the natural extension of the alpha continued fractions, but only for alpha greater than or equal to 1/2. So again, this case that was well understood when Nakada introduced the alpha continued fractions in his original paper. There's a natural question as to whether or not there's somewhat of a unifying family which contains both of these families, the alpha continued fractions and the S expansions. So the first part of the talk will be an affirmative answer to this. So this is what we call contracted Farey expansions. So I'll describe these continued fraction algorithms. And then in the last part of the talk, we'll zoom in on a certain family of contracted Farey expansions, which we call superoptimal continued fractions. And these are motivated by Bosma's optimal continued fractions. Okay, so we talked a little bit about singularization. So this is a way of accelerating continued fraction expansion by removing some of its convergence. But this technique is somewhat limited. So it dates back to Lagrange from 1798. But it has two main restrictions. So if you start with the regular continued fraction expansion of x, you can only singularize and remove the nth convergent if the n plus first partial quotient is equal to 1. So you can only singularize and remove a convergent if you see a digit equal to 1. So you can't remove just any convergent that you want with singularization. And then this first restriction actually puts another restriction on singularization, namely that you can't remove two consecutive convergents. So you're performing something of a local surgery on your continued fraction expansion, and when you do this, this kind of messes up the neighboring partial quotients, and you can't remove two in a row. Okay. But there's a more general acceleration technique called contraction that seems to have been somewhat overlooked, at least in the dynamical community that studies continued fractions. And this is due to Seidel from 1855. And what it does, so you start with a generalized continued fraction expansion, and it basically produces from this generalized continued fraction expansion a new one whose convergence are any prescribed subsequence of the original convergence. Okay? So you start with a generalized continued fraction expansion, pick any subsequence of strictly increasing non-negative integers that you want, and then you can produce a new explicit continued fraction expansion whose convergence are precisely that subsequence of convergence. Okay? So this removes both of these restrictions, 1 and 2, from singularization. You can remove any of the convergence you want and as many blocks of convergence as you want. Okay? So I say it's been overlooked in the dynamical community. So it seems that people are aware of this result of Seidel, and it's used in the arithmetic theory of continued fractions. But even there, it's usually in a restricted sense. So usually this subsequence is sequence of even or odd integers. Okay? So it's not usually used in full generality. So this raises a natural question as to whether or not all of the alpha continued fractions are realized sort of as S expansions together with contraction. So we have this more powerful technique where you can remove any convergence that you want. So can you realize all of the alpha continued fraction natural extensions just with this more powerful technique of contraction? And the answer is no, you can't. So this is essentially explained in an introduction by Nakada and Natsu from 2008. And at the end of this introduction, they state that the convergence of the alpha continued fraction expansion of x are not necessarily a subsequence of the regular continued fraction convergence. So you can't necessarily start from the regular continued fraction expansion, remove convergence, and then get the alpha continued fraction expansion. Okay? So there's no hope of just realizing the alpha continued fractions with contraction itself. But there's another system, another slower system, where we'll find that we actually can do this with similar techniques. And to do so, we need to introduce the Farey tint map, which is an interval map with two branches defined as shown. So on the left of one half, strictly increasing, the right of one half strictly decreasing. And you can also study the system dynamically with the measure with density 1 over x. Now this is an infinite but sigma finite invariant measure that makes the system ergodic as well. And this system has been called the mother of all continued fractions, at least up to isomorphism. So there's another continued fraction map called the Laner map, which generates what are called semi-regular continued fraction expansions. And this was called the mother of all continued fractions in a paper by Karma and Core. Because starting from the Laner expansion, if you perform singularization and kind of its inverse procedure called insertion, you can generate all semi-regular continued fraction expansions of x, starting from the Laner expansion. So via this isomorphism between the Laner map and the Farey map, we also consider the Farey map the mother of all continued fractions. And also via this isomorphism, the Farey map generates continued fraction expansions. So to see this, I'll make a couple of remarks. So first, let's fix some x with regular continued fraction expansion a1, a2, a3, etc., and fix some n. One can show that the nth point in the forward orbit of x under the Farey map can be written as a Mobius transformation acting on x, where the entries of this Mobius transformation can be written in terms of the regular continued fraction convergence of x. Okay? So there's these funny indices lambda n and jn in this matrix. These are coming from the following relation. So again, we fixed some x with regular continued fraction expansion. We fixed some n, and the lambda n and jn come from taking as many of the regular continued fraction digits as you can, add up as many as you can, plus some remainder to equal n. Okay? So that's this lambda n and jn, this expression. And one can show that the Farey expansions, so the continued fraction expansions generated by this Farey map, the convergence, which we call Farey convergence of these expansions, are precisely the left-hand column of this matrix A0n here. Okay? So the left-hand column, the quotient of the left-hand column. So I'll denote this by un over Sn for the n minus first Farey convergent, and this is precisely this fraction of this form. Okay? So if you notice, if lambda n is actually equal to 0, so you get rid of this term, you run through all of the regular continued fraction convergence of x, and then for non-zero lambda, you obtain what are called the mediant convergence of x. So the Farey expansion is a semi-regular continued fraction expansion of x, whose convergence are all regular continued fraction convergence and mediant convergence. Okay. So the Farey map also has a natural extension. This was introduced in 1989 by Shunji Ito. Here again, the domain is the unit square. And the map, script f, and the density, the invariant density for the natural extension can be given explicitly. And this is ergodic because the underlying Farey map is ergodic. Geometrically, what this does, so we split up the domain into the same vertical rectangles and horizontal rectangles as before. And what this natural extension map does, if you're in the left half of the picture, and you're in the intersection of some vertical rectangle and some horizontal rectangle, so in this case V2, H2, the map will send you down and to the right one intersection of rectangles. Okay? So if you're in the left half of the picture, you get mapped down and to the right one rectangle. If you're in the right half of the picture, the map will map you up to the top half of the picture. Okay? So this is kind of geometrically what's happening with this natural extension map. Okay. So there's a natural correspondence between orbits under this natural extension map and the Farey convergence that we saw before. Okay? So really, we're studying this two-dimensional system, but we're studying it to understand real numbers. So we'll just look at points starting from this top ledge of the form x, 1 and study their dynamics. So we'll associate to the nth point in the forward orbit under this natural extension map the n minus first Farey convergent, which we're denoting by un over Sn. Okay? As an example of this correspondence, if we start with x with regular continued fraction expansion 423, 423 repeating, and we start with x comma 1 on the top ledge of our picture, I've also given out the sequence of all Farey convergents. So there's going to be 4 corresponding to the first 4 in the regular continued fraction expansion, and 2 corresponding to the 2, 3 corresponding to the 3, etc. We associate to the 0th point in the orbit, the 0th Farey convergent. This is sitting here on the top ledge. We're in the left half of the picture, so we go down and to the right, go to the next Farey convergent. We're in the left half of the picture, go down and to the right, go to the next Farey convergent, down and to the right, the next Farey convergent. Now we're in the right half, and we get flung back up to the top. Okay? We go to the next Farey convergent, and we're in V2 intersected with H1, because the next digit is a 2, and we continue this procedure. So go down and to the right, we're in the right half, get flung back up to the top, down right, etc. Okay. All right, so we briefly mentioned inducing transformations with the natural extension of the Gauss map, like Kraaikamp did for S expansions. We can also get induced transformations of Ito's natural extension of the Farey tint map as well. Okay. So for this, we'll fix some measurable subregion R of the domain. We'll assume that it has non-zero and finite measure, and we'll let f sub r denote the first return map to R. So in sub r will be the hitting time to R. And from ergodicity of the natural extension map, we also get ergodicity of the induced system, R, the Borel sigma algebra, mu bar R, fr. And here the measure mu bar R is given by taking the mu measure of a set S divided by the mu measure of the set R. So this is the induced measure. And since we've assumed that R has non-zero and finite measure, this will be actually a probability measure in our case. Okay, so the system is actually, I said it's ergodic, it's also conservative. So one can show that almost every point, so if you fix some measurable subset R with positive measure, almost every point from the domain will enter R infinitely often. Okay? I mentioned earlier that we want to really start studying points on the top ledge in the form x comma 1. So it's possible that this whole top ledge belongs to the null set of points that don't ever return to R, or don't return infinitely often. Okay? But if we put the further restriction that the interior of R has positive mu bar measure, we can guarantee that Lebesgue almost every point from that top strip will actually enter R infinitely often. Okay? So using this induced map, the map f sub R, this naturally determines a subsequence of the forward orbit of the point x comma 1 under the map script f. So you take the forward orbit of the point x comma 1 and just look at the subsequence that's entering the region R that we specified. Okay? So this is giving us a natural subsequence of the orbit determined by our space R. And via the one-to-one correspondence from the previous slide, we naturally get a subsequence of the Farey convergence of X as well. Okay? So this is just the corresponding subsequence that we pick out when we enter R via this one-to-one correspondence with the convergence and the orbit. Okay. So now we come to our definition of contracted Farey expansions. So the contracted Farey expansion of a point X with respect to a measurable subregion R of the domain will denote with these superscripts R, and this is just the contraction of the Farey expansion of X with respect to this subsequence that we've picked out from this forward orbit entering R. Okay? So we start with this Farey expansion, and then we're going to produce a new continued fraction expansion, this contracted Farey expansion, whose convergents are a subsequence of the original convergence. And the subsequence is the subsequence from the previous slide, the one picked out by the region R. Okay. So it's basically a corollary of Seidel's result that the contracted Farey expansion of X with respect to R has precisely that subsequence that we picked out. So this is just Seidel's result and some bookkeeping of notation. Maybe more interestingly is that these digits, alpha in R, beta in R, can be described explicitly in terms of the dynamics of the induced system that we are studying. Okay? So we don't really need to know the Farey expansion of X in order to compute the contracted Farey expansion of X. Right? So we can actually compute the digits of the contracted Farey expansion of X just from the induced system. So each of these induced systems is really giving us a continued fraction algorithm to produce this contracted Farey expansion of each X. Okay, so associated to this induced system, we will have an isomorphic system, which is essentially a two-sided shift space for contracted Farey expansions. So I'm going to make some somewhat technical assumptions to simplify things in this statement. So recall there's this matrix A0n. So this is coming from really the one-dimensional Farey map. So recall the f n of x can be written as this matrix A0n x inverse acting as a Mobius transformation on x. And this n sub r of z is the hitting time to r. Okay? So our little n here will be n sub r of z. Denote the entries by ur of z, sr of z, tr of z, rr of z. And the assumptions that we'll make for this slide are that r is bounded away from the bottom line y equals 0, and that this bottom left entry is equal to 1. One can show that this implies that the top left entry is either 0 or 1. Okay? Now we define a map phi sub r from the region that we're inducing on to the plane, depending on whether this top left entry is 0 or 1. So it has two different maps, depending on whether the top left entry is 0 or 1. This map is injective off of a set of measures 0, so we can use it to obtain an isomorphic dynamical system. We just push everything through this injective map. Okay? So our isomorphic dynamical system will be denoted omega r, b, nu bar r, tau r via this commutative diagram. Okay, so if you start now with a point of the form x comma 1, whose contracted Farey expansion is beta naught r, alpha 1 r over beta 1 r, etc., look at the image of this point under this isomorphism map, big X comma big Y. This map tau r of the isomorphic dynamical system is essentially a two-sided shift on the contracted Farey expansion. Okay, so in the first coordinate, you're just forgetting the first digits. In the second coordinate, you're keeping track of those digits. So this is very similar to what Hitoshi was mentioning before. Furthermore, this push-forward measure for this dynamical system, so nu bar r, has density 1 over the mu bar measure of r times 1 plus xy squared. So if you recall the slide from the natural extension of the Gauss map, this density should look very, very similar to the natural extension density. It's not a coincidence. So in 1996, Brown and Yin showed that the induced system on the region H1, so this top half, if we look at the induced system with the natural extension of the Farey tent map, this is isomorphic to the natural extension of the Gauss map that I introduced earlier. We actually find that this two-sided shift space from the previous slide is precisely this representation of the natural extension of the Gauss map. Okay? So this map, this isomorphism phi sub H1 is precisely the isomorphism of Brown and Yin, and the two-sided shift is precisely the natural extension map for the Gauss map. Moreover, the subsequence of convergence that we're picking out with this subregion, so if we apply the slow Farey natural extension map, pick out the subsequence of convergence where we land in H1, the subsequence is precisely the regular continued fraction convergence of X, and the contracted Farey expansion of X actually recovers the regular continued fraction expansion of X. So everything kind of works as you would expect based on the Brown and Yin result. We also find the S expansions from this construction. This should be natural to assume. So the S expansions are constructed via these two tools, singularization and induced transformations of the natural extension of the Gauss map. Contraction generalizes singularization, and the natural extension of the Gauss map is sitting within the system. So we have all the tools to generate all of the S expansions from Kraaikamp. There's one little subtlety. So the region that we need to induce on, we can't just take the isomorphism from the previous slide between the top half H1 and the natural extension of the Gauss map. We also have to compose with the natural extension map. So this is due to the fact that from the previous slide, these convergents that you're picking out in the top half have indices n minus 1. So this extra power of g is kind of taking care of this to give you indices n, essentially. Okay. And then we also see the natural extension of each of the alpha continued fraction maps as a specific induced transformation here as well. So if we pick some alpha between 0 and 1, we'll define the domain in a couple of steps. So the first step is to define an integer for each point z in the top half h1. So this integer is defined as follows. We look at the induced map f sub h1 and look at the minimal number of times we need to apply the inverse to our point z to land to the left of alpha in the region h1. So that's this integer k of z. And we let a be the set of points in h1 for which this k of z is odd. So I've drawn an approximation of a here for alpha equals 1/4. So it's somewhat of a fractal-like set. And then the region R is defined in terms of A. So this formula might be a little bit hard to parse. Essentially what you're doing is you're taking the region A, cutting it along the line x equals alpha. So in this case, alpha equals 1/4. We're cutting it along this line. We take everything to the right of our cut and push it down and to the right as many times as possible with the map script f, okay? With the natural extension of the Farey map. Okay, and we can show that this induced system, so on this particular R constructed in these lines, is the natural extension of the alpha continued fraction map. Okay. So this gives a new definition, or a new construction of the natural extension for these alpha continued fractions. And the proof, again, uses this two-sided shift space that I talked about before. So one can show with this two-sided shift map. So for this particular example, this would be the domain under the image of the isomorphism map. With this domain, when you project down onto the x-axis, you see the one-dimensional alpha continued fraction map. So it's immediate to see that the alpha continued fraction map is a factor of this induced system. Okay, so in the last few minutes, I want to talk about another particular family of contracted Farey expansions. And these are kind of inspired and motivated by Boltzmann's optimal continued fractions. So I've talked briefly about semi-regular continued fractions, but haven't really talked about what they are. So this is a subfamily of these generalized continued fractions that have been the basis of this talk. And these semi-regular continued fractions are just generalized continued fractions whose digits satisfy certain criteria. So it's a certain subfamily of generalized continued fractions. And then one particular instance of a semi-regular continued fraction would be the regular continued fraction. So if we take some irrational x and two relatively prime integers p and q, and denote by theta x p over q, this quantity q squared times the difference of x and p over q. This is called the approximation coefficient of x and p over q. And this is giving us a measure of how well the rational p over q approximates x relative to the size of the denominator of q. Okay. one can show that for almost every x, and any semi-regular continued fraction expansion of x with convergence pk over qk, the supremum of these approximation coefficients is always greater than or equal to 1/2. Okay? So you might get some approximation coefficients that are very, very good. You might get some convergents that approximate x very, very well, but they can't all approximate x very, very well. So the supremum is going to be greater than or equal to 1/2. One can also show that the semi-regular continued fraction expansions cannot converge too quickly, so in the following sense. So if we look at the denominator of the semi-regular continued fraction, and look at the regular continued fraction denominator, the convergent denominators that it sits between, and denote these by the indices by n of k. So notice if you actually start with the regular continued fraction expansion of x, this n of k would be equal to k. So you'd be looking at little q here. If we look at this ratio is really comparing the growth rate of these denominators of our semi-regular continued fraction expansion to the growth rate of the regular continued fraction expansion denominators. Right? And one can show that the lim sup, as k goes to infinity, of this growth rate is bounded by log 2 over log g, where g is the golden ratio. So semi-regular continued fractions can converge quicker than regular continued fractions, but not too quick. So it's bounded by this upper bound. So in 1987, Bosma introduced an algorithm to produce what are called optimal continued fractions. So these were actually introduced by Slade in 1960. Slade used this idea of singularization, again, where you start with the regular continued fraction expansion of x, and you can singularize to obtain the so-called optimal continued fractions. Bosma's algorithm, you don't need to know the regular continued fraction expansion of x to begin with. So it gives you a geometric algorithm to produce these expansions from scratch. And these satisfy basically the optimal case in both 1 and 2 here. So all of the approximation coefficients are less than 1/2. And this limit of the growth rate is actually equal to log 2 over log g. It's equal to this upper bound. So the optimal continued fractions give you the best approximations and the fastest convergence among all semi-regular continued fraction expansions. Okay, but if we kind of extend our view from semi-regular continued fractions to these more generalized continued fractions, we can improve both of these criteria arbitrarily well. Okay? So if we fix some epsilon and c greater than 0, we'll call a generalized continued fraction with reduced convergence pk over qk epsilon superoptimal if all of our approximation coefficients are less than or equal to epsilon and the lim sup of this growth rate is greater than or equal to c. We have arbitrarily small approximation coefficients and arbitrarily fast convergence. One can show that the approximation coefficients of x and its Farey convergence are related to the dynamics of the point x, 1 under the Farey natural extension map. So in particular, so I've drawn several curves in this picture, epsilon equals 0, epsilon equals 1, 2, 3, 4, etc. These are given by this equation 1 minus y over x plus y minus xy. And this set S sub epsilon is a set of points for which this expression is less than epsilon. So in particular, this shaded region would be S sub 1. And for the other values of epsilon, it's the region above the curve drawn by epsilon here. Okay? So one can show that your approximation coefficient of x and the nth Farey convergent is less than epsilon if and only if the nth point in the forward orbit under the slow Farey natural extension map lands in this region S epsilon. Okay? So if you land very close to the top of this picture, then you have a very good approximation coefficient, very small approximation coefficient. Okay? So with these ideas, we find that if you fix some epsilon and c, let these be arbitrary positive numbers, take any measurable subregion, positive interior, it's a subset of S sub epsilon, and make it small enough so that its mu bar measure is less than or equal to log 2 over c, then the contracted Farey expansion of x with respect to r is epsilon c superoptimal. Okay? So for any epsilon, any c, we can get arbitrarily small approximation coefficients and arbitrarily fast convergence. Okay? So yeah, there's one small caveat with this theorem, and it's that we only have this statement for almost every x. So there could be a null set of x's that we don't have returning to this region R infinitely often, and so this contracted Farey expansion is not actually defined for a null set of x. But we can get a nice statement for all x, and this follows from a couple of results, classical results. First is due to Legendre. It states that if your approximation coefficient is less than 1/2, for any x and any rational p over q, then that rational, in fact, has to be a regular continued fraction convergent of x. And the second result is due to Hurwitz, and it states that for any x, there are infinitely many rationals p over q for which the approximation coefficient is less than 1/√5. Okay? So with Hurwitz's result, together with Legendre's result, we find that these rationals p over q that satisfy this criteria must in fact be regular continued fraction convergence of x. Okay? So as a corollary of the statements from the previous slide and these two results, we now let the region R be S sub 1/√5. By Hurwitz and Legendre's result, and the proposition from the previous slide, we know that for any x in 0, 1, it's irrational. The forward orbit will actually return to this region S sub 1/√5 infinitely often. So the contracted Farey expansion of any x is actually defined. And if you compute, so epsilon would be 1/√5 in this case, you can compute the measure of the region R and find that for c equals √5 log 2, then this contracted Farey expansion is epsilon c superoptimal for these values of epsilon c. And the Farey convergents that you're picking out as the subsequence are precisely the rationals from Hurwitz's theorem. And this is very similar to Minkowski's diagonal continued fractions. You essentially replace this 1/√5 by 1/2, but this improves the diagonal continued fractions. All right, so I will stop here, and thank you for your attention.